we can apply some of these ideas to the Young's so-called Young's double slit experiment, which I will produce here. In 1803, Thomas Young presented a paper at the Royal Society of London on his work that generally is credited with making the acceptance of, or the general acceptance of the wave theory of light was attributed to. Now, nowadays, it's very easy to reproduce the experiments. You just get a laser, you shine it into double slits, and you produce an interference pattern on a screen that you can look at with your eyes. Thomas Young, in his day, look here, is 1803. He's got to get a coherent light source, impinge it on a double slit so that the distance of separation is comparable to not a whole lot bigger than the light, and then have some width to it. Thomas Young was probably one of the greatest geniuses that maybe has ever lived. He is truly remarkable. You ever get some time, take a look at well, at least read an autobiography or a biography of him, or at least look at a Wikipedia entry or something on him. But Thomas Young did this, is probably most famous for this Young's double slit experiment, at least in physics. But it's the same person, same Young, for Young's modulus. He also is responsible for what's called the Young Laplace formula for capillary forces, and also the critical angles of fluids on interfaces. And so he was really well versified. He also worked on translating Egyptian hieroglyphics, and he worked in other areas. So he was truly a polymath and very across all disciplines. But I'm going to think of it for us as like a modern day experiment. It was no mean feat in his day, first of all, to produce a plate here with slits in it, parallel slits. And it's kind of interesting the way he does it. He coats a plate of glass and then uses a screw to inject some grooves in it, and these vertical grooves then become the slits that it goes through. From a top view of this, I'm going to be looking everything in plane wave approximation, but the plane wave coming from our light source here, so far enough away that if I have a point source, it's here. These are presumably the peaks of the waves. And so when they hit the two slits here, S1 and S2, top and bottom, and that they are separated by this distance d, the sim between the two slits. I think of these as really point slits. And so by Huygens principle, these become the secondary spherical wavelets. And so long as you're very, very far away over here, in the case of a laser beam, you could be across the room, and these slits may be a few microns apart. But you come over to here. You have a detector, which might be your eye, and in the case of Thomas Young, it was. By the time it gets over here, these spherical wavelets, the plane wave approximation is good. It's far enough away, so this R is many, many, many wavelengths. And so this the light from the top slit comes up here, and the top light from the bottom slit comes here, They travel slightly different distances, which I've got listed here as R1 and R2. And they get detected here, get recombined in your detector with the total wave that's hitting here. Okay? Wherever they hit, I call that the center of your eye of your detector is the height X. Now really you would scan around these. These would be almost from the center here. Okay? Would be almost a radius, but in practice you have a screen that's very far away, but you're looking so close to axis that you're basically projecting all this on a screen, and you're at a height X on that screen. So that's sort of the case depicted here. And again, by the time they reach the detector, you've got E1 from slit 1 and E2 from slit 2. They came out of a wave, and they're the exact same peak, and so they're going to have the same amplitudes, assuming that these slits are exactly the same width, but of negligible width in this case that we're looking at. And this wave comes over here. It's going to be E naught I K R1 because it travels this distance minus omega t here. The phase it's at is exactly the same phase as this one, so I can, it's since they're both coming in at peaks, and so the phase factors are, I can set that to 0, whatever the phase is over here. And we have E1 equals, total E is E1 plus E2. And as we've seen from the previous segment, the combined intensity was given by this expression here, where delta now is just the difference in the R2 and R1. We can make some approximations. This is what Young did, in fact, was R1. Well, if you look at our diagram up here, R1 would be this horizontal distance, which I'm calling L, I think. Let's see if I called it L. Yeah, I called it L. So get the total distance here to the screen is L. It's really R. I mean, I'm thinking of it as this radius here, but by the time you get to the center portion, that's L. Yeah? And so you get the distance from here is L. The distance to where your detector is X. And if you've got this distance between the slits as little d, then this, and it's exactly centered here, then this is d over 2. And so the distance vertically is d over 2 is x minus d over 2. That's for the top one, and then you can expand that out. And the bottom one is similar. You've got the horizontal distance L to the screen, and the distance now is x plus this additional piece that is the leg of this triangle to get R2 is x plus d over 2. And expanding those out, and then take the difference, R2 squared minus R1 squared, and you get L squared minus L squared over here, x squared minus x squared, d squared over 4 minus d squared over 4, but the cross terms, xd, it's minus a minus xd, and so this total distance here is 2xd. And this you can factor into R2 minus R1, R2 plus R1. And now then, for small angles, and generally these are the one, by the time you project this on the laser version of the experiment, this might be several meters, and this distance might be several microns. So we have a very small angle, indeed, over that whole span. And for small angles, then R2 and R1, when I add them together, well, they're approximately equal to 2R. That's the, and so one can use that approximation that R1 plus R2 is 2L here, and 2XD. The 2's cancel, and then you can solve for R2 minus R1, and that's just X times D. Which is kind of a nice expression because our difference, our phase difference delta is K R2 minus R1, so it's just Kx d, and then usually at some point one converts this to 2 pi over lambda for the wave number. And we just plug that in for delta over here. Now, there's some approximations involved, but they're all very, very good in the regime that this experiment's done in. You get some cancellation, but essentially you get this result here. D and lambda are constants, as is pi, and then x we think of as a variable here. So you can get the maximum, you can get the minimum. If you plot this function, this cosine squared as a function of x, you get a bright the central maximum. It comes down to 0 in between. There's some terminology associated with it. What you would see here, I'm plotting intensity this direction, is that you get high intensity, and those appear bright, and so these peaks here are what are called bright fringes, and ordinarily you just see sort of a blob of light over here. And the dark fringe is anywhere that it comes down to 0, and so those you would see as black. What that means is that you would see for these two slits, you get the following interference pattern. Here I've got the penciled in portions as supposedly where the light is, and in between is the dark portion. Two important things about this. One was, first of all, you can't get this phenomenon, or it's not very easy to get. You just really have to do some handstands to get a particle theory of light, which is the dominant one because of Newton prior to Thomas Young. But by demonstrating this experiment and showing that the wave theory predicted it, and also that the phenomena occurred as predicted by wave theory, people generally started accepting more and more of the wave theory of light. So it's credited with being the deciding factor in converting everyone to a wave theory of light. Once you have that, then for the bright ones up here, let's take a look at that. You want this to be equal to 1 to get the maximum. And at a maximum, I know that this argument, so that the cosine becomes a 1, has to be an integer number of pi. It's squared here, so you can either have a 180 degrees, minus 1 squared is 1, or 0 degrees and its multiples. And so if you set those equal, or set that equal to an integer times pi, this argument, the pi's go out, and you could solve for the distance between the slits, or the distance between the fringes, and get this. Or, more importantly, probably what you would do is measure the distances between the slits. You would know the order number. These m's are called the order number. You could use a micrometer to measure the distance between the slits. So if you know X and M and D, then you can get the wavelength. And so another important aspect of Young's experiment is that once you accept the wave theory, then you can use it to determine what the wavelength of the light source is. And so it can be thought of as a way to measure wavelengths. And so people did that once they were convinced that light was a wave, and found, of course, the very short wavelengths that are in the 500 nanometer type ranges. So very, very short wavelengths, and um, which gave even more credence to the theory.